Okay, I'm going to go with you guys because you're on the right. I don't know. So come on up here. Do you have a computer to plug in? Yeah. All right, I'm going to fire this up. I'll give you what I have.
You need anything? You have an HDMI port, you'll be okay. Yeah, that's good. Okay. There's a switch over on the right wall.
What's on the wall?
The wall, this one right here?
Yeah, just point it down.
Alright, so let's start. Today we're gonna present you the EMV. EMV is short for Europay, MasterCard, and Visa. And the task of our group is to analyze the protocol and to suggest a few improvements to speed it up a bit. Okay. So the overview of our presentation, it's a short presentation, is going to be this. I'll introduce the EMV, what it is about, why we use it, how we use it, and afterwards Matt will present you the EMV transaction flow and the security of the EMV, and subsequently Josh will end up our presentation with the EMV performance and enhancements. Right. So the EMV is an international payment standard using smart cards. It was introduced by Visa and MasterCard in the 1990s in order to mitigate skimming fraud. And EMV is not a single protocol, it's more a collection of applications and protocols. And now Matt is going to present you the transaction flow.
Okay, so EMV is how you pay at the end. One of the methods, the smart chip is how you pay at the end of a transaction. So it's very important to note that this has to happen at the end of a transaction, unlike a strip. A strip, you can just pay whenever you want in the transaction. You can just swipe it and it'll be fine. But with the chip, it has to be at the very, very end. So the first step is application selection. So that actually happens on the terminal. Most of this actually happens on the terminal itself, not your card. The card only really holds data. It's essentially, the way I equate it to is it's essentially a flash drive with a bunch of files. And it isn't aware of what it holds. It just knows it holds stuff. So the first thing that happens is application selection. Each card holder, card purveyor like MasterCard, Europay, all like the card distributors, they all have their different methods of pay. And each method has its own protocols and set of steps it has to go through. So the first step is determine what method of pay is happening. Once that's been decided, the card then dumps all of its information, all of its files over to the terminal in order for the terminal to read what files it actually needs in order to complete the transaction. The next two steps are data authentication and card holder verification. So these are, we'll talk about this in a little bit, but essentially these are just determining that the card is authentic and that you are who you say you are and you are the holder of the card. The next two steps, processing restrictions and terminal management, are fraudulent protection, just to ensure that this transaction isn't fraudulent. This is a real transaction. The card isn't expired. It conforms with the current the current most up-to-date applications, and everything looks fine. The next stage, when it comes back up, is terminal action analysis and first card action analysis. So the terminal will then review everything it's seen and determine, is this an okay transaction? Is this fine? Does everything look fine? Does everything match up correctly? And will then propose to the card, and it's specifically the terminal proposing to the card whether or not it will do an online transaction or an offline transaction, which is really important. The card will then accept or completely decline and that the transaction. If it's an online transaction, there's additional stages that have to be made. There's additional processing, additional verification that has to be made in order to ensure that this process is in fact a valid charge. If it's offline, it'll essentially just say, all right, cool, we're good. We've decided that this charge is in fact valid, and then we'll move on and continue, and that's essentially the end of the transaction. If it's online, there's additional processing, additional verification that's done. Then it's proposed again, is this an okay transaction? And it will accept or not, and then it'll say, that's the end of your transaction. So for card authentication, the verification and type of transaction we just mentioned, card authentication has three methods. There's static, dynamic, and combined. So static and dynamic are standard and must be included on every terminal. Static is essentially a symmetric key. It's just there to determine, it's there to ensure that the transaction is safe and valid, and it uses a symmetric key with the bank in order to determine who this charge is being attributed to. The dynamic, however, is only used to authenticate the card and the data that travels with the card's signature. It's not able to sign a transaction. It's not able to. It's just all it can do is sign that the data in the transaction is valid. Finally, we have the combined version, which holds both of them, which is it's combined. It uses both of them in order to ensure that the transaction is valid, the data is all signed, and that the symmetric key is it's essentially all valid. The verification stage. So with credit cards, if I don't know how many of you have credit cards versus debit cards, or how many of you have both. But with a credit card, you've never. I guarantee none of you have ever had to put in your PIN or sign for anything on it. Well, probably not sign, but you've never had to put in a PIN, because I'm assuming most of us are, you just don't have to put in a PIN. I don't know why. But with debit cards, you do.
That's actually only here.
I know. Yes, you were right.
Here in Baltimore, here in the States?
No, here in the States, it's only credit cards don't have a PIN. With debit cards, they do have a PIN. But this was specifically related to credit cards. So in most cases, you don't have to put in anything else to verify your identity. It's just none, and it just accepts it, and it thinks that's fine. However, in the cases of debit cards and in other locations, you have to give either a signature or a PIN in order to verify that you are in fact the cardholder. Finally, there's the type of transaction, online or offline. This determines how much more verification is done and when the transaction is attributed to. Josh will then now talk about the performance of the EMV card. Yeah.
So, hello. So obviously the EMV protocol was not really designed for speed and more security. From the research that we've seen, it takes an average of about 15 seconds to complete a transaction, which can be a long time if you're right in the grocery line, you're itching to get out of there. And so one of the reasons for that is the application selection process takes a while, because each card has its own proprietary method of selecting, of determining how to complete the transaction. Sorry. And also, as Matt stated earlier, the entire application file locator must be read, and what that is it's like a list of different methods to be used, like Visa Pay, Visa, MasterCard, things like that. So that whole thing must be read in order, and then the terminal decides which thing to actually use. And then finally, the transaction must happen at the very end. So as the grocer bagging up, you can't just swipe the card and it'll let you pay. You have to wait till he finishes, and then you put your card in, and then does the whole transaction that Matt described earlier. And so these are some possible solutions to enhance the EMV protocol that Visa and MasterCard already sort of came up with. One of them is Quick Chip from Visa and Chip Fast from MasterCard. And basically it just allows for easier, early removal of the chip. When you put the chip in, you can take it out before the a whole thing has been completed, and also it supports all the cardholder verification methods that Matt has described. And yeah, I think that's the end of our presentation.
I know this was really quick, but does anybody have any questions? Yes?
So for the fast chip, does that mean that when you remove it, it's basically still encrypting and doing everything even though the card is not present?
Yeah, so like oh, you want it?
Yeah, essentially it'll take all the data in and then it'll continue with all the transaction stages. So it doesn't need the card to be in there the entire time. It'll just continue on. So something scary about this is the fact that, well, you're having your card's data being read by a terminal. And terminals are, as we saw from the Target Act a few years ago, these terminals are pretty vulnerable. Does that answer the question?
Yeah, thanks.
We're also doing a paper, so if you want to read that at some point in the future, be sure to send it to you.
So did you look at the crypto protocols, the actual exchange of information between the client and the server and the card?
They're proprietary.
There's nothing out there that explains any of this?
Not from what we found. We found this a paper that describes it all, but it's in general terms from what we saw. They are ISO protocols, but like the actual meat of it is proprietary. In the prompt that was given, what was specifically mentioned was that these transactions are slow. But personally, I've never actually felt that these transactions were slow, so I thought that was a little odd. And so we may have looked at this in a different way from how it's working. So originally thought by slow you meant that the actual time it takes for all of these cryptographic functions to complete is time consuming. And while they are in fact time consuming, the thing that I found most time consuming was actually the fact that in comparison to the swipe, in which case you only have to swipe and then you're done. The chip you have to wait until the end of every transaction, and then you have to, and then so it's not, the way I equated it was essentially instead of paying in parallel to while you're in parallel, you're paying afterwards. So it's additional time, which I think is why the perceived slowness of these transactions is coming from.
So why do you have to do it afterwards? What fundamentally do you think?
It needs all the data.
Okay.
So a magnetic strip on your card is very easily obtained. You can just, and it's static data. It's very much, it is the definition of a symmetric key. It is there and it never changes. And once you have that, you can do whatever you want with it. Which is why we had so much credit card fraud, because people would just take take magnetic strips, copy them, and then use them. And that's how you'd have so much credit card fraud in the past, the past decade. Now with the chips, they're much harder to reproduce because of their complexity. There's actually a case where where immediately after these were introduced, these cards were cracked. There's and we use it in reference. These cards were cracked, and somebody had put in a. This is actually a police report that was read. Somebody had made a programmable version of this, a programmable EMV chip, and it was this small, tiny little computer with set bytes. If you want to look it up, it's EMV cracked, and they go into the whole list and even show you the difference between the size of the card. So the cards are usually they're super thin, they're set millimeters. This card was much thicker by like 4 times the amount. Even still, it's still, in your normal hands, you wouldn't really notice the difference between something that's only 22 millimeters thick versus something that's almost 100 millimeters thick. It's kind of difficult to notice the difference. But that was one of the things that they noticed was in this case was that this card was much thicker, much heavier, and the chip had been was soldered on.
Okay. So I was wondering, you're done with the main presentation?
Yeah.
Okay. So I was wondering if you guys, just to put you on the spot a little, so you don't have the actual protocols. Could you imagine for us, and maybe we can do this as a class, what these protocols could actually look like if you have a digital signature, signed key on the card? Right, so forget about the application. Like that stuff is just kind of, you know, BS.
Well, I'm assuming you mean this stage here.
I'm just talking about the authentication stage.
Okay.
Yes, that's the one. So here, pop up the bulletin board. I want to see if we can at least kind of sketch out what like that transaction would look like,
Sure, go ahead.
and why it would be the case that you need all this
This up, right?
offline signature.
Do you mean to actually write it on the?
Yeah, just put it on the board. So on the board, right, there's three parties. We have a card,
Yeah, right here.
and you guys are welcome to like contribute to this. This is not just all for them. So we have three parties. We have a card, we have a terminal,
Yeah.
and we have somewhere in the back end we have the banks.
Yes, correct.
Okay.
So we have I guess we'll.
Here, you can turn off the just pull the switch. Pull the plug. Cool. Okay.
Card, terminal, bank.
Okay.
So
Good.
we have the card, the terminal, and bank, and so with this first one, which was the static method, it has to. I equate it to essentially the strip where it never changes. However, these keys are shared by the card and the bank, so they're
Okay.
hard coded. So you have, I'll just call it S key.
Mhm.
I'm not able to really write small on a blackboard. So these two cards are these two keys are held by the terminal, by the bank.
By the bank, not by the terminal.
Yeah, but not by the terminal. However, this is where I'm a little confused on this, is because it's specific it's very explicit in how it states how this transaction is done. Is that it's very explicit that all of the data, all of it, is transferred over to the terminal.
Okay.
All the files. So
maybe those files don't have secret data. Maybe they're just like information about what the card supports.
yes, I believe that those files I believe are specifically related to the application that is attempting to the method of pay. So, for example, one of the examples I could think of is like Visa has this method called Electron, which I'm not entirely sure what it is, but I'm assuming it's kind of like tap pay versus chip pay. So there's a different way of authenticating the card based upon the method it uses.
Why would there be, or anyone, why would there be a difference in a tap pay versus a chip pay? In terms of how you'd have to design this protocol. What's the fundamental difference between the tap pay and the chip pay? Yeah.
You can't run operate like computation on a tap.
Maybe you can.
Well, all the computation is, well, that's actually, there's very minimal computation that happens on a card. The only computation on the card that happens is if it decides to accept a transaction or not accept a transaction.
Okay, so it's going to do something like sign something or max something. And it's only going to be able to send back that response during the very limited time when you've tapped. So when you've got something inside of the slot, it can sit there and talk to the card repeatedly throughout the entire transaction. But with a tap pay, it's got to be like talk now or forever hold your peace.
Yep.
Okay, so with something where you have tapping, so you have a very limited opportunity, a very limited window to actually talk to the card. How do you build that out of this system? Like, what are the actual messages that the terminal has to send, and where do they go?
Well, in the case of a tap, it would have to be, you'd only have the amount of time to send one amount of data.
Okay.
So you're only...
So we can send a round trip. I can send some data to the card immediately sends some data back.
Yes, you really only have maybe one amount of conversation.
What would you put in that conversation?
Well, you'd have to send in all of your application data.
Okay.
So you'd have to send in, well, actually that's not true. You wouldn't have to send in all your application data because you wouldn't have enough time for that, unless the data is tiny.
I think he has
Like,
something.
whenever I've used the tap thing, it like isn't like instantaneous. It does take like maybe half a second or something. So it could. I feel like I don't know. I'm not an expert.
I've never
I
used the
imagine it
tap
could be
function, so
done.
I don't know. So yeah, you could have enough time to actually send enough data through.
Could you keep like a key association to some sort of database where you know like what the user is available to use, or like how much money the user has, and all the card has to do is transmit a key that you hash into the database, that database? That make
Yeah,
any sense?
Yeah.
in
It's sort
relation,
of an identifier.
yes.
Yeah, intuitively, if you've got that brief of a contact, you've got enough time to make a request, get a response, but you don't have enough time to do heavy calculations. So it's probably doing nothing more than just, hey, send me your key, getting that key back, and then using the key to sign and transmit it.
So what's the
From the
vulnerability
terminal.
if you're just sending a key into the terminal? What's the vulnerability there?
Well, I mean, you guys.
Well, I mean, some kind of radio interception.
Okay,
Or
that's
replay.
possible. Or malware in the terminal gets that key and then
Yeah, I mean, you implicitly trust the terminal,
And
Well,
every
not all-
but you also
do
trust.
you trust the terminal? That's the question. Do you trust the terminal? Why
Technically,
Uh,
you are supposed to trust the terminal due to, it's essentially the third party.
Okay.
Because, I mean, you're technically just between the bank and your card is the true connection happening. The terminal is supposed to be your third party, your third trustworthy party.
But what if it's not? Like, do we
I mean,
actually trust terminals in practice?
I don't,
Okay.
but.
No, I don't think we should. Because again, think of all the scenarios where you could see that terminal. We're not just talking Walmart where there's, a video camera on it. You're also talking, the drive-through. You're also talking, the flea market where people can set something like that up. So, no, I would not trust the terminal.
Okay, so let's say the terminal sends a message to the card.
Mhm.
What's going to be in that message?
The terminal sends a
Yeah,
message.
let's say, well, maybe the card sends some initial message. We do some
Probably a
rewrite.
challenge.
Okay, a challenge. But is there anything else that's going to be in there? Like, are we going to include the amount? Are we going to? What are we going to put in there? Let's say the only thing the card's going to do is produce a signature on some data or a MAC on some data.
Since the EMV is a collection of protocols, it's
Right.
probably the terminal will ask the card which kind of protocol it supports, like
Okay.
which.
So let's say that stuff gets done, and now we're ready. We know what kind of protocol it supports. What are we going to send to the card? Anyone? Yeah, go ahead.
It's here. I want to spend this amount of money.
Okay, and I am
Target, and I want to spend $70.
good. Okay, so let's say that's our first message. I mean, there may be other messages before that. So let's say the terminal says to the card, "Hey, I'm a Target point of sale terminal. I want to spend $70."
So target.
Mhm.
Nothing from the terminal
the-
to the card.
Yeah, sorry, from the terminal to the card. Let's go that way.
You want to erase it?
No, it's good. So.
See, writing on the board is way less fun than it looks.
No, I never.
That's I don't know, a capital M for money.
Yeah. Put a dollar sign next to it. Would be good.
Okay.
Okay, so this is great. So we've got the first message. It's two things. And the card is going to send back what?
Card
If
is
it has
gonna-
the amount, then okay. If it doesn't, then.
Does the card even know how much it has?
Yes, actually, there's
It
a
does.
floor limit.
Ah, okay, good.
Well, I don't really understand the meaning of a floor limit. It seems more like a ceiling
Okay.
to me. But it is called a floor
So the
limit.
card will not let you spend more than like $10,000.
Well, yes, it's like.
And actually, the tab one has a maximum thing,
Okay.
as far as I know.
Okay, okay, good. So the card does some kind of check. And then the card, if it likes the amount, if it thinks everything looks kosher, it sends back what?
It says it should send back that it's fine, spend it now, or
Do we do anything with that key?
Isn't that kind of status like okay or something like that?
Okay, we could send okay, but do we do anything with that secret key you guys put in those cards?
I mean, you have to have the secret key in order to send it to the bank. You have to sign or encrypt
Good.
a message to your bank in order to say, hey, I'm spending this money. Transfer money over to this location.
Okay, if it's a symmetric key, what primitive are we going to use to actually, yeah.
A Mac?
Good, okay, so a MAC would work really well. So we send a message that maybe includes, we just MAC the T and the dollar sign even, and we maybe add an OK message to that. And then we put a MAC on that whole thing. And then if we send that to the bank, if the terminal sends that to the bank can be like, everything looks pretty good, right? This protocol seemed pretty good for us so far?
Well, I mean, we're assuming that this is an online transaction at the moment.
Right, we are.
If it was an offline transaction,
What would it do?
what would it do? The terminal would just accept, the card in the terminal would accept the transaction. The floor limit would be added onto the card.
And the card would keep that.
And the card would keep that value, and it
How-
would essentially just transfer over and over and over until it reaches a terminal in which it's an online transaction.
So how does my terminal know that the card has actually accepted the transaction and it's not a fake message from a fake card? Like how do we do that? How do we make sure?
Well, that's why you have the second method, the dynamic method.
Good, and the dynamic method uses?
Public and private keys.
Good, so we can look at the public key of the card and we get a signature instead of a MAC and we can verify it. How do we know that that signature actually belongs to a legit authorized card? How do we know, like someone gives me a public key, card says, hey, here's my public key and here's a signature with it. Like, how do I know that's a real public key of a card that I should accept?
Maybe there is a transaction between the terminal and the bank itself.
What's that?
Maybe there is a transaction.
Oh, if it's offline.
If it's offline.
Oh, it's
okay.
offline. Oh.
How do we know it's a real card?
Well, I mean, then you have the card holder verification as well. That's why you have the what you know as well.
Okay, but how do we know that this, I mean, just because a card says here's a public key and someone types in 1234 into the PIN pad, doesn't mean it's a real Visa card. How do we verify that this is really a card issued by Visa? This public key? Yeah.
They could back it up with a signature authority, like a certificate authority.
Okay, so what would be on the card? So a certificate saying this public key this card is issued by Visa. Here's the expiration date of this card. And now, if we get a valid certificate, we trust it. That sounds like a pretty reasonable.
Well, that's what, if I can go back to the slides, I briefly, very quickly went over this. But after this stage right here, you have the, if I can get this up again. So here at the processing restrictions and terminal management, it ensures that these, can you repeat that one more time, that quick thing that you were saying?
Certificate.
Certificate. So it ensures that this is a valid, that it is valid here.
Got it.
So here, back to the first stage, you have the stage in which it determines what method of pay. So each method of pay is different. It's a 5-byte signature or a 5-byte amount. Then it has to read it, and so down here is where it actually verifies that this data is, I guess, kosher.
Okay, got it. So we can only do that if we're using the dynamic method, the public key method. We can't
Correct.
do that if we're, okay. Okay, the last question from that protocol you guys scribbled up there. What stops the point of sale terminal from sending that same transaction into Visa twice and getting credited twice for the same amount? Like, what in this protocol stops that attack?
Well, I guess that's why I'm so worried that people swipe the card twice.
But I mean, just once. So like I put it in once, that gets charged once. What stops someone from just replaying that signed message to Visa?
There should be a unique identifier for each transaction.
Okay, good, good. And so how do we guarantee that? Who generates it?
I mean, I guess the terminal should be the one who generates it.
Okay, good. Okay, so we could do that, or we could have the bank generate a unique identifier as a challenge at the start of the protocol.
Well, the bank can't do that because in the case of like for example, in the case of an offline transaction, there's no interaction between the bank and the card.
An offline transaction.
In an online transaction, the bank isn't actually contacted until the very end.
Okay, got it. All right, good. All right. So yeah, I just wanted to kind of walk through the different possibilities.
No problem.
These are the things to actually talk about a bit in your report, like what are the implications. Cool. All right, great. Thanks.
Thank you very much.
Who is up next?
I know you said you had a fever, but are you going to be available for office hours?
Yeah, I'll be on this afternoon.
Okay. If not, I can call or email or something.
Okay.
That's I just wanted to make sure I meet with you.
Yeah, we do it tomorrow. Just
That's no problem. I understand.
keep watching people, whatever.
Yeah, no problem.
Oh, it's over on the wall to the right of the board. Just pull it down.
Okay.
Don't let it go for too long or
I had no idea.
There you go. But then when he gets, there's no way to hear it. You might want to go down a little bit.
This works.
Okay.
It does, right? Yeah. So alright, hey guys, so we have done a talk about protocol analysis of Telegram.
we are going to analyze the protocol the Telegram uses. It's called MT Proto, and we are going to analyze how it holds up based on security principles like confidentiality, integrity, and availability. So Telegram is a messenger. It is advertised as a messaging application which provides secure communications. To make the application fast and secure, fast, reliable, and secure, the developers developed and implemented their own crypto algorithm, and it was called MT Proto. The application right now is very popular. It has over 100 million plus monthly users, and over 15 billion messages are delivered daily. Even though the application is considered a safe alternative, the protocol has been in question since its inception. This is primarily because the developers decided to use old primitives instead of the currently accepted standards. The protocol was theoretically proven to be not INT-CCA and INT-CTXT secure. While the client source is freely available, the server-side software is closed source and proprietary. So let's talk about the protocol being used, called MT Proto. Telegram uses its own encryption scheme called MT Proto, which is meant to be computationally fast on mobile devices and with no compromise on security. This is accomplished by using older primitives and by combining them in such a way that older attacks do not apply. So there are multiple primitives used, which are Diffie-Hellman key exchange, SHA-1, key derivation function, and AES-256 in IGE mode. Now, as you look at this, you would realize some of these primitives are really old and broken. For example, SHA-1, we just some time back saw SHA-1 collision. There's AES-256 in IGE mode. But the way the protocol, the developers intend to use this is they use them in such a way that these older primitives are combined and the current attacks, they do not apply. So the protocol works in two modes of operation called cloud chats and secret chats. Moving on to cloud chats. So cloud chats is a default mode of operation. It's all the messages are stored on the Telegram cloud. So encryption is done using AES IGE. So let's talk about how the protocol works. So we have the main payload. The payload is concatenated with the session ID and the salt, and the AES, the data to be encrypted is encrypted using AES. The AES key and IV are derived from two separate keys. The two separate keys are, one is a persistent shared key, which is exchanged via Diffie-Hellman, and the other one is a message key, which is basically a SHA-1 of the payload, session ID, and the salt. And these two keys are put into a key derivation function, which uses multiple iterations of SHA-1 to generate the AES key and the IV, which are used to basically encrypt the payload, and we get the encrypted data. We add the message key, which happens to be hash of the payload in there, and we also have an authentication key ID, which is basically used to verify the shared key between the client and the server, which is a symmetric key, and it's the 64-bit, the least significant 64 bits of the SHA-1 of the shared key.
Wait, don't go back. Go back to that last. Is that, okay, that's still here? Okay, sorry, jump. What in the world is going on here? Like,
all right.
I'm not trying to interrupt you. This is not like a criticism of you. I'm trying to understand.
Okay. So these guys used a lot of primitive functions to make a protocol which is supposed to be secure and fast. So how do you make something fast? You use old protocols. So they use multiple iterations of SHA-1.
Okay, but whatever, the SHA-1, right? SHA-1 is a hash function. It's a little broken. It's a little old. It's starting to get weak. But whatever. Like, what are they even trying to accomplish?
So what they basically want is that they want a new key for each and every message. That's the main thing they are trying to establish.
Okay,
so
I get it.
If you have like a proper session key and you use it in AES CBC or something like that and have that session key for an entire session to encrypt all messages, then they think about attacks such as IND-CCA or IND-CTXT. Their basic claims towards IND-CCA and IND-CTXT is that, hey, we use a new message key, we use a new key for each message since we derive the key itself from the message. So that's one of their basic things.
So can you walk me through decrypting this? First of all, I want to be convinced that this even decrypts, and then I want you to walk me through what happens if somebody tries to like change the message as it goes over the wire. Because I think that's what they're trying to do, right? Is build Mac. I'm not trying to put you on the spot. But let's together.
So
they don't have a Mac, but
okay.
Yeah, they don't have a Mac.
There's no Mac, but they're doing this crazy thing with SHA-1. They're hashing the payload, which is the message. So that must have something to do with integrity, right?
Yeah.
Okay, so let's just I just want to walk through this one time. So we hash the payload plus all this other crap, and we get SHA-1, some SHA-1 thing. And you said this auth key ID is part of that SHA-1?
It's basically for the authentication. So in this particular protocol, what they do is the server is authenticated using its RSA certificate, but the client technically doesn't send its RSA. So how it authenticates a client, or how it's technically believes that it's the one who initiates the chat, is that it sends a random nonce encrypted, which is then used for the mutual encryption under AES-IGE. That is how it just believes that it was definitely the initiator of the chat. And some other steps that we'll go through.
Yeah, we're going to talk about them.
Okay.
But, so if you're talking about the decryption, how it will happen is basically once it reaches the other end, it uses AES-IGE for the decryption, and once it gets the decrypted payload.
One more thing, like he's just specifically asking what is fed into the decryption function.
Okay.
So you take the SHA-1 of the message what the user provides, and that is fed to a KDF, whereas the same thing is also passed as part of the entire message.
Yeah.
So the receiver takes this, feeds it back to the KDF, and the receiver already has the share.
Also.
So again, he's going to end up with these things.
Good. And they decrypt the encrypted data using this crazy IG mode.
Yes. So they specifically use
only used by Telegram, this IG.
Yeah, and specifically IG is used because in IG they use knowledge of two previous things. Like generally in CBC or something like that, we just use either the plain text or the ciphertext from the previous block, right? Whereas in IG they use the plain text and the ciphertext from the previous block.
And what is the guarantee? What property is that giving?
So for error propagation.
It basically indefinitely propagates the errors, is what they claim.
So if I change what you're saying is if I change any bit of the encrypted data field, this goes over the wire, and then somebody tries to decrypt it using the right key.
Yeah, it's going to destroy all the blocks.
Every subsequent block, including that one, is going to get trashed.
Right.
I like that. Okay, good.
Yeah.
Continue.
Well,
why does that give me guarantees that the messages? How do I check? Like, how do I guarantee that the message can't be trashed? Like, we don't have a Mac here, so what is guaranteeing that if somebody did try to change the ciphertext, we can detect
the integrity?
that? Yeah. How are we getting?
So once you decrypt and you have the actual payload, then you take its, then you actually SHA it and get the message key again, and you've already received the message key that was sent by the initiator.
Good.
Over there in the.
Because it's there in the message as well.
I know I'm totally interrupting your presentation. I will let you go forward in a second. Are you telling me that I can't? Anyone in this class, can I change any bit of this encrypted data, and I will get caught? Do you guys believe that or not? Okay. Does anyone see something I can change in the encrypted data that might allow me not to get caught?
I was just thinking, doesn't SHA-1 have like a lot of collisions?
SHA-1 has very hard to find collisions. Let's assume that it's too costly to find collisions in SHA-1 right now. So the argument here is if I change anything in the encrypted data, then the decryption is going to get trashed. Oops, you guys lost that. And then when I when I decrypt, I'm going to hash. Oops, I think you got to go back one.
Oh.
When I hash the salt session ID payload that I decrypted, it's going to give a different message key, and that's not going to agree with the message key that was in the message. I don't know whether this is all true. Does anyone see anything that I could change in the encrypted data that would not even be hashed in? Okay, good. So there's 15 bytes of padding at the end. If I change any bits back there, it's literally not going to have any effect on the decryption procedure at all. I can completely mess with those. So this doesn't mean there's a real attack there, but like clearly this thing isn't even like well.
That's exactly what.
Yeah, that's exactly what cryptographers and all researchers say, that
this is theoretically insecure because the padding is not accounted for.
Okay.
And I can go ahead and change any bits, and then the receiver would not even notice, because what it will care about is what is the payload length.
Yep.
And after the payload length, everything that is there, it won't even check the length nor the actual pad bits. It will just discard it right away.
And how long, you say it's 0 to 15 bytes of padding, but does it really have to be 0 to 15 bytes of padding? Could it be short? Could it be longer than that?
It has to be a multiple of the AES block size.
Okay, but could you have like 100, in the actual code, could you have 100 bytes of padding?
just has to be a multiple of the.
Yeah, multiple of the block size.
So the minimum size, the minimum padding that makes it a multiple.
Okay.
Is what's used.
Okay, so I would just look at the actual code and see if they actually enforce that. That would be one
Okay.
thing.
Okay,
I'll stop
then-
interrupting your
okay.
presentation. Okay, this is crazy. This is nuts.
Yeah.
This is not what you should be doing, but continue, go ahead.
Moving on, the other mode is secret chats. Secret chats basically provide end-to-end encryption, which means only the two clients which are exchanging the messages, they have the keys, and they are the only ones who can read the messages. These secret chats are device specific, which means the keys are only stored on the end-to-end devices. So if I want to use my Telegram account from a website to view my messages, I cannot do that because these are device specific. So this basically works the same way. The way this works is it works over another layer of encryption of empty proto, and through that layer it provides the same function, and key exchange happens through Diffie-Hellman between the end devices, and it's basically the same thing again. It also provides features for self-destructing messages based on a timer or when the sender or a receiver deletes them, and it's also available for voice calls.
Okay, so I'll talk about how the auth keys are generated. It uses Diffie-Hellman key exchange, which we are all aware of. It's almost the same step, save one or two. So I'm going to explain the whole process. The client first generates a nonce of 128 bits, and it sends across to the server. In this particular message, there's nothing else of significance except the nonce itself. What the server does is it sends across a string which is a product of two random prime numbers p into q, and it also sends its own server nonce. Along with it, it also sends its RSA public key fingerprint because, as I mentioned earlier, the server will be authenticated using the RSA public key fingerprint, so it has to send it across to the client for that. And obviously the client nonce itself to just make sure that it was the right server that it reached to. The client performs something which is called a proof of work. What it does is basically it factorizes the string p into q and and derives two numbers p and q such that p is less than q. And this p is actually the mod p, the prime that is used in the g to the a mod p. And it sends a new nonce to the server, which is it performs a proof of work, and then it sends a new nonce which is encrypted under a shared key. That is the, I think I marked the, that's correct. So it also sends across p and q in the next message, and a new nonce. This new nonce is encrypted under the RSA certificate, the public key that the server just sent across. Why this new nonce is required is because the client up until now has not sent anything by which the server can authenticate it. So this new nonce is sent across so that now server can encrypt the rest of its g to the power a or g to the power b mod p, and then send it encrypted. So nobody on the wire can decrypt and try to forge it. So once the new nonce is sent across to the server decrypts it using its own private key, the RSA private key, and now both client and server are in possession of the new nonce. They carry out the computation to find the AES, the temporary AES IgE key and IV. The AES IgE is the same protocol that we discussed. That we discussed previously. So they use this new nonce to calculate their temporary AES IgE keys and IV, and using those keys, they exchange their g to the power a mod p and g to the power b mod p. And now this is the actual shared key that will be used between the client and the server. So after this step, both the sides calculate their g to the a b mod p, and all the temporary data is discarded. So all of the previous data that was exchanged will be discarded. And the auth key can be either temporary or permanent. If the server chooses, it can send an expires in field with the nonce, which basically just says that after this particular period of time it will expire, and then the client and server have to redo this particular process.
Sorry, can I interrupt for a sec?
Yes.
So is that the proof of work is to factor P and Q?
Yes.
And that's from the client?
That's from the client.
So empty proto is designed in mind to make it fast. for encryption and decryption, and so that's why they're using old primitives.
Yes.
And it's designed such that clients that are old, so old mobile phones can do that as well.
Yes.
But if the clients have to do the proof of work,
it's just a 64-bit string.
But what's the point of doing proof of work over here?
It's basically like a DOS prevention, so that nobody can send a new nonce right away.
There's no digital signature or something which can verify the presence of the client.
The essence that the client is there. So there's no digital signature, or so it could be like a lot of entities trying to connect to the server. So they have this just one bit of step to verify that the client is a legitimate client trying to get the service.
So knowing what you know about picking prime numbers and all that stuff, does this make a lot of sense as a way to do a proof of work on the client side? Why not?
Factoring's expensive, and like, if you want to make something fast, the last thing you want to do is force the client to factor a giant prime number.
But on top of that,
it's not giant though. It's only 64.
Okay, it's not big, but you have to find P and Q, right? The server has to find new P's and Q's all the time, which isn't necessarily that easy. So you're going to do a lot of work on the server. So even if you just wanted to do a proof of work, and we talked about using proof of work like client puzzles, you could just use a hash function or something instead of doing this craziness. So this is just a little weird, but at least it makes sense. Does the rest of it make sense? What's going on with this?
Yeah, what I don't understand is why do you have to encrypt GA? Like, isn't the point of Diffie-Hellman that you don't have to encrypt the GA and the GB?
Can someone explain why are we encrypting this GDA and GB?
But you don't have a digital signature as well. So it's just like because anybody could take that G to the A, and then, I mean, the classic man-in-the-middle attack that we saw for the Diffie-Hellman will not be prevented unless you have either of these mechanisms. So you don't have a digital signature, so this is the best that you can do.
So is that technically signed G to the A?
It's an encrypted G to the A. So it is encrypted under RSA, RSA public key that.
So yeah, a lot of people have tried this, not using signatures, using encryption instead. And I guess the idea is that the man-in-the-middle attacker can't decrypt that GDA, so they can't run their attack. It might work, it might not. I mean, I don't see any obvious problem with it, but it looks really stupid. So, okay, yeah, well, that's weird. Continue, go ahead.
So yeah, like we discussed, server authentication is a very general RSA public key authentication, and client is authenticated. It's not a very technical authentication mechanism. It just assumes that because this entire procedure that we discussed previously has new nonce, and all going across using that shared auth key, that is how it just believes that it must definitely be the initiator of the chat who is now speaking to me. So now let's talk about how perfect forward secrecy is maintained in Telegram. So in secret chats, what happens is this particular shared auth key that you have established, it'll be valid for either a week or for about 100 messages, whichever happens first, provided you have used that key for at least one message. And once the key expires, you redo the Diffie-Hellman key exchange and establish a new nonce. Sometimes when you have a permanent auth key, which is established when you do not send a timer or an expires arg field, what happens is it just tries to redo the G to the A computation over the same new nonce. Then it doesn't recompute the new nonce, but it still recomputes the G to the A, so that the ultimate G to the AB mod B is different for every 100 messages. Yeah.
Okay, yeah, so as we spoke about this a few minutes back, so it uses AES-IG, which is actually an obscure thrown away protocol. The initial intent, I guess, of this protocol was to bring in authenticated encryption, but finally it was replaced by things like AES-GCM, and the only property which we saw was that it has this forward error propagation, and that's why Telegram uses it, because they don't have something else to maintain the integrity of data being passed through. And Christy, as you asked, Telegram claims that they have this protocol only for messaging and not for sending large files. So that's why they are ready to create a new key for each and every message. If it's for large files, that might not work out properly.
So files are not encrypted?
No, files are encrypted,
Yeah.
but since it's for small messages, they are okay to generate a new key for each and every message so that the process can be passed. Yeah, so this procedure requires AES IG specifically requires knowledge of two things. Generally, you have an IV and then you keep feeding the ciphertext in next block in most of the blockchaining modes. But in this case, you need two non-existent values, so kind of two initialization vectors. As Shikha and Apur mentioned, it is theoretically not secure against IND CCA. But what they claim is that we generate a new key for each and every message, so that doesn't apply to us. As in, definitely they do agree that the cryptographic algorithms which are being used by them are broken, are definitely broken. But the way they have implemented it is not broken.
That feels good.
So yeah, so they don't believe in things like encrypt then MAC or MAC then encrypt, nothing like that. And yeah, and the message key is sent as part of the final payload, and that message key is again used to feed it into the key derivation function and derive the AES keys. You can see it over here. And then finally, they have a key fingerprint in the client end-to-end encryption method. And this fingerprint is not the one which is used for key visualization. Like when you verify that both of us have actually reached at the same symmetry key. This is just for some sanity check and to ensure that you have actually reached at the same AES key and to avoid things like developer mistakes. Yeah.
So there have been a lot of analysis going on over this protocol, and there's definitely a lot of people who believe that it is not a secure protocol. But up until now, only theoretical attacks have come to surface. In fact, Telegram also has the bounty of about 200,000 bitcoins worth of bitcoins. Sorry, for anyone who actually breaks the protocol. So.
No, they actually had it in 2015, and they gave a closed system. So their server-side closed code is completely proprietary, so no one can look at that. You can see the messages being transferred, and based on that, it's not really breakable.
We got 20 days.
So as we have discussed previously, it is definitely insecure under the IND CCA. Your pad length is not checked, or neither are the pad bytes. So you can actually mess with the padding in the encrypted message, and yet the server would not really care about it. What they claimed was if it were an implementation where the server was sending across decrypted bytes, even if the pad length was different or the pad bytes were different, then it would have been a blatant protocol misuse. But the implementation actually is that the server doesn't respond at all if it finds out that there's something wrong with the message. So on the client side, it'll see that the message has been sent, but on the server end, it won't even realize that the message has been received or there was something of that sort. I mean, on the other user end. There's something called blockwise adaptive chosen plain text attack. The AES IgE mode is not secure under it, but then again, because every message uses a different key, they claim that this is not something that we need to be worried about. SHA-1 is broken, yes, but they don't really use SHA-1 for any kind of identity purposes. So they say that this is not what we are concerned about. What about replay and mirroring attacks? So if we go back to the cloud chats.
Do we have another? How many more people do we have to present today? You guys are the last?
think.
Oh, okay, then continue. Sorry, I just want to make sure.
So yeah, over here if you see the in sequence number and out sequence number, the way they calculate these numbers are that these bits will be, so if there are two parties speaking A and B, and if A is the receiver, B is the sender, then when A receives the message, this particular the out sequence should be 0 for A and the in sequence should be 1 for A. So if I capture a message and then try to mirror it, I mean, definitely replay is not possible because they have sequence numbers, but even mirroring is not possible because now even the direction is being accounted for. So that's...
Yeah, and we also read a research paper where they came up with a modified version of Telegram.
Who did?
What is that?
Oh, it was a researchers, some researchers.
Yeah, some researchers from Europe or...
Yeah, I don't know.
Yeah, it's just some sort of modification, not much. Basically, they propose to use AES counter mode for faster performance. The problem with AES IG is that you cannot parallelize it at all, since it depends on two things from the previous block. So they wanted to use counter mode, but at least what I feel is that researchers, they didn't understand the actual intent of Telegram for using AES IG, because they claim that AES IG might provide authenticated encryptions due to the high forward error propagation. So I'm not sure if researchers knew that was the actual intent of Telegram. And one more main thing is that they want to bring in this concept of name coins. So name coins is a big utilizer of blockchains. So there's this system called DANE, DNS-based authentication for named entities, and which has picked up a lot of recognition in the last 4 to 5 years. So it prevents one of the main problems in public key infrastructure, where you depend on a certificate authority to give attestation for a public key. What DANE does is that as part of the initial DNS response, it tells you whether what the public key of this particular IP address is and whether that is valid or not. So Namecoin, what it does is it utilizes DANE and puts it into a blockchain. So every entity on the network is now part of the Namecoin blockchain. So if I want to communicate with, say, Apu, I'll initially ask the Namecoin blockchain for Apu's identity. And yeah, so since it's a blockchain, they presume that proof of work and those things will be higher than that, and that can be considered more secure. And yeah, so and to eliminate the key exchange mechanism to stop man-in-the-middle attacks, what they propose is that once we get the identity information for public keys from the blockchain, we encrypt the you generate a session key, you encrypt the session key using the peer's public key and send it over to the other guy. Yeah, so of course the challenges with this is that again the researchers didn't understand the actual purpose of AES IG mode in Telegram, and of course the normal problems in blockchain, like what if you have more than 51% of the resources in your network. So, and here are some references, and that's all. I know you're very sad at what Telegram has done with their protocol.
Yeah, I mean that's just nuts, but okay, cool. Well, I mean it's wow. So I hope you guys are paying attention because these are good exam questions. Yes, go ahead.
I think this application is so popular. I mean, I had never heard of it until now, but
because of end-to-end encryption.
Is that it? I mean,
this was literally the first application which provided that.
Oh.
It came just after WhatsApp.
Okay. So what? I mean, I've used something like Wicker before, which I assume is like one of the most secure of these types of applications. Why do you think that? Is it just the accessibility factor, or the fact that it was first? It
was first.
Definitely the fact that it was first did play a role in it, but because I mean, even if you dive deep into it, there are a lot of claims over it's not secure. But,
yeah, but
at the end of the day, nobody has really been able to...
Were you speaking about Pigeon or Wicker?
No, well, Wicker is the only other application like this.
Okay, but do you know if it has like a new message, a new key for each and every message?
Every key is...
Because that is like a very critical property these guys claim. And that's why even terrorists love Telegram.
Telegram is also not hosted in the United States, which I think
it's made by this Russian guy.
Yeah.
Yeah.
Who lives
and
in Germany.
It's non-profit by the way, and the server code is completely proprietary, so you don't know what they're doing on server code.
Got it. That's making me feel good. All right.
To stay away.
How do you verify? So you do this Diffie-Hellman thing with your co-person. How do you verify that you have the same key?
Yeah, so it generates a key fingerprint on both sides. It's a combination of SHA-1 and SHA-256.
Got it.
And then you see...
It's some bits of SHA-1, some bits of 256, and then... So it's just a way to send the key, but not just... I mean, not really the key, just an identity of the key.
Got it, okay.
So normal off-the-record verification scheme.
So we had an exam question in the last midterm on people doing some kind of key fingerprinting, right? And finding collisions and not very good key fingerprints. Can you find collisions in these fingerprints?
No, not at least in key fingerprint for telephone.
Okay.
Because they use the complete SHA-256 and not a part of it. So that's the other fingerprint you're talking.
Can you pull up the picture?
Fingerprint which every client checks whether they have arrived at the same.
Can you pull up the picture just on Google of what that Telegram key fingerprint looks like?
Yeah.
Because I think it's helpful for people to see what they actually do.
Actually, I can show it to you on my.
You can just do images. I bet there's one up there.
Yeah.
Okay.
Something like that.
Pull up one of them. Okay, so could you guys, if you had to compare your key fingerprint with somebody else to make sure you got the same one, could you use that graphical key fingerprint? Do you think that's usable?
I'd make a mistake.
Yeah. So it seems to be 3 shades of blue. 4 shades of blue, and you'd have to get it right. And if it was a little close but not exactly right, would you be guaranteed that you were not quite getting it right?
But you can also verify it using this.
Yeah.
Okay, good.
We have this.
Okay, so, but let me ask a question. So let's say that you got, in real life, you got...
I think you can actually stamp those things.
Okay, yeah, I think you are, if you're in the same room with the person who was doing it. But if you're not, and you're just kind of like reading it over a phone, or you've sent it over email, or through some other app or whatever. So let me ask you a question. If somebody tried to get a man-in-the-middle position and was messing with the key fingerprints, they couldn't spend enough time to get it exactly right, or even close to right, but they could just get some of the digits to be a collision, maybe the first couple or the last couple, and maybe get a picture that looked kind of vaguely like the right one. Would you guys actually, how many digits would you check before you quit and said these are the same 2 fingerprints?
Depends. Like 5, 6.
Okay.
Depends on what messages I was sending, and what my threat model was.
Okay.
If like I was like, yes, I know the NSA is targeting me and is trying to.
You're gonna check every digit.
I'm gonna check every digit.
Okay, I wonder. This is not I don't know the answer to this. I'm just curious how many people who even bother to check these fingerprints actually check more than like the first 2 digits, the last 2 digits, and say it looks okay. Because it would be possible to find a collision in a fingerprint for those 4 digits, maybe not for the entire thing. Anyway, interesting.
But we won't compare 2 bytes, really.
You think you just need to do 2 bytes?
No, I mean, like, if you look at it, what, like 16 times 16 byte? 8 times 4, 32 bytes. So that if you do that in a 64-bit machine or use, vectorization.
It seems like you're trying to find a collision on a 256-bit value. It seems hard. But you might be able to get a few bytes here and there.
Well, I mean, making collisions fine. I'm just saying comparing the full key isn't expensive.
Oh, yeah,
4
probably.
stores and 4 loads if you're using a good vector size.
Yeah, you might be able to look at the actual key. That's true. All right, thank you guys. Awesome.
Thank you.
Cool. Okay, well, we are at the end of class. So, yes, Wednesday.